name is Caitlin Didier, and today I'll be talking about molecule polarity determined by vector sum of bond dipoles. First, I'm going to display a few very important definitions that everyone needs to be aware of before talking about this subject. Bond polarity is a separation of charge which is measured by its dipole moment. Dipole moment is when two atoms in a molecule share electrons unequally. Dipole is two charges separated by a distance. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. And I'm showing you here that molecule A has a partial positive because it loses some of its electron density, as atom B gains some of its electron density. It gains a partial negative. And as you can see, the pair of electrons are much closer to atom B. I also want to show on the board now that if one atom has a lot more electronegativity than another atom, it creates an ionization, and that's how we get an ionic bond. And that can be denoted like this. If B hogs all of the electrons, then we just get a whole positive charge here and a whole negative charge there. And that would be an ionic bond. So now I can go into showing you some polar bonds versus some nonpolar bonds and how you can figure that out using the vector sum of the bond dipoles. As you can see here, we have formaldehyde, and I'll draw over here a minimized electronegativity chart because I can't draw the whole thing, but you can easily look one up online or in your textbook. But as long as you remember that fluorine is the most electronegative atom, that's all you need to know because everything else increases towards fluorine. So if this was fluorine on the periodic table, everything increases up towards fluorine on the periodic table and to the right towards fluorine as far as electronegativity, but fluorine is the most electron negative atom. So knowing that, we can determine what will have partial positive and partial negative signs on any type of molecule. So for example, here, we know that hydrogen is way over here on the periodic table. It's not going to be as electronegative as carbon, nor as oxygen. So we denote this partial positive and this partial negative with an arrow pointing towards the more electronegative atom. And you can remember which one's positive, partially positive, because the end of the arrow kind of looks like a plus sign. And so we would do the same thing for this hydrogen and carbon bond, but we also have this carbon-oxygen bond, and we know that oxygen is closer to fluorine, so we would have to draw this because this would be partially negative and this would be partially positive just for this bond. So now we can take those three individual bond dipoles and do the vector sum to get the overall molecule dipole. So if I'm taking this arrow here and then adding this arrow to it, and then I'll add this arrow to it, which would be pointing something like that, we can see that the net would be this long one here. And it's pointing straight to the right. So the overall net, I'll draw in red. So this would be the net dipole for the whole molecule due to this vector sum. So that is this arrow right here. And that makes it polar because it has a net dipole moment. And we can do the same thing for water, which is a very common molecule. We know that oxygen, due to its position on the periodic table, is much more electron negative than the hydrogens. So we would denote that with an arrow pointing towards the oxygen, like this. And we would use the same vector sum notation that we just did, the head-to-tail method, and add these two together to get the vector sum dipole moment for the whole molecule. So we would have this arrow, which is this one, and add this one to it. So the net would be going straight down. So I'll denote that in red. This would be the net, which is this one. And that makes it polar as well, because it does have a net dipole moment. Okay, another example I can show is HCN. We know from looking at a periodic table that carbon is going to be more electron negative than hydrogen. So we would draw that with an arrow like this, the plus sign over the hydrogen pointing towards the carbon. But then we also know that nitrogen is more electron negative than carbon because it's closer to fluorine on the periodic table. So we would have to draw another arrow like this, pointing towards the nitrogen. So if you just add those up, you know, they're just going to add together like this. And so the overall net is going to be pointing in the right direction. So this is the overall net when you add them together, since they're just side by side, like that. And that's not actually typical for all linear molecules, so that's why this particular example is interesting. So that's just some polar, but now I'm going to show you some nonpolar. CO2, carbon dioxide, is a common example due to its linear setup. So we know that the oxygens are more electronegative than the carbon. So when you draw your arrows, they're going to be actually pointing away from each other. So that makes this, if you think of these as vectors, you have a 180-degree angle between them. This is 180 degrees. And if you were to add them together, they would actually cancel out. So that means that this particular molecule has individual bond dipole moments, but it doesn't have a net dipole moment since these two cancel out. So that would make this nonpolar. Because the individual bond dipoles cancel out and there's no net dipole moment. So I'll show you another example of that. C2Cl4. Okay, we know that Cl is more electronegative than carbon, so you just write the arrows like we've been doing for all of the individual bonds. But note here, for the carbon-carbon bond, it's the same exact atom, so therefore there's no difference in electronegativity, so therefore there's no dipole. And therefore there cannot be a dipole moment in between these two atoms. But for the CCl bonds, there is bond dipole, but if you take them individually and add them up, you're going to get a cancellation. And if you just look at them, you can kind of see that they're all going in equal and opposite directions. But I'll go ahead and do the vector sum for this one. This is this arrow, and then we can add on this one to it. Actually, let me do it over here in case I run out of room. So this is this arrow, and you add on this arrow to it. And then you add on that arrow to it. And then you add on this arrow to it, it goes back to the same starting position. So you get a full circle, which means they all cancel out. There's no net dipole moment for that either. And so I hope you know the difference between polar and nonpolar now and know how to do the vector sum.